So today I'll be talking about mechanisms of robust visual working memory representation, and I kind of already gave a sneak preview of the next slide earlier when I accidentally pressed the wrong button. But here's kind of the idea, right? So in everyday life, let's say you're on your way to a meeting, you're running a little bit late, you see that taxi, you might want to remember it and keep in mind where it was. Then you see someone in the crowd who looks like a friend that you know. In this case, you're like, hey, what's John Sorensen doing in New York City, right? He shouldn't really be here. And so there's this constant mental gymnastics going on of, I'm on my way to a meeting, I'm going here, maybe I should change my direction. And so there's lots of things that you want to remember at any given time. In this case, for example, the car, what color it was, where it was located, where it was heading, how fast it was going, but also, let's say, the identity of your friend's face in this case. Like, did you actually see your friend in the crowd? And so that's kind of what I want to talk about today, which is the idea of working memory as a central workspace of the mind, which supports behavioral goals flexibly and robustly. And I'll get into that a little bit more later. But first, I want to talk briefly about how this central task is being performed in the brain. And I really like this quote. I actually got this book from Frank Tong when I left the lab. 3 books, I believe it was, from William James. And it turns out that everything we're doing right now, he already did way back when. But he had the following suggestion, right? So he said that the same cerebral processes, when aroused from without by a sense organ, gives the perception of an object, will give an idea of the same object when aroused by other cerebral processes from within. Kind of a modern instantiation of this would be what we call sensory recruitment theory. And so the overall idea here is that you have some kind of high-level behavioral goal. Let's say in this case, you're trying to remember a face of a friend that you saw in the crowd. And what you might do is then recruit an area of the brain that's good at seeing faces. So let's say visual cortex. And there you can have this really highly detailed visual representation of that face. All right. So flexible and also robust, which is really the point I'm going to try to make next. And this is just going to show some work that I've done in the past, really in a sort of bird's eye view. So working memory has this gradual loss of detail. So for example, if you're remembering the face of your friend from that crowd, and if you have several delay durations, let's say ranging from 1 up to 12 seconds, then over time your memory error will become larger, right? But the thing to note here is that your memory error gets larger, but not that much, right? Just a couple of degrees. One other nice demonstration of this is that when you show distractors during a delay, they warp memory. So in this case, the task might be something like this, where you're told to remember an orientation. Then during the delay, what happens is you see another orientation. It's totally irrelevant and you're told to ignore it, right? And then after the delay, what you do is you give a reply. What happens when people do this is that what you see here, they have some kind of memory bias, right? So the mean response that they would give is biased as a function of the difference between what you have in mind, so what you're remembering, and this irrelevant distractor. So what I call this distractor offset. And what you see in terms of this bias is that you get this slight attraction towards the distractor, even though it's irrelevant, right? So while there is gradual loss of detail and some sort of systematic biases that emerge in working memory, I think the overall point that I'm trying to make here is that the biases and the decay right over time is quite small. So working memory is super robust. And why is it so robust, right? What are these mechanisms of robust visual working memory representation? That's what I'll be talking about today. So let's briefly step back to the sensory recruitment theory, which might be a little bit simplistic if you think about it. And it served, I think, cognitive science really well for a long time, and it had some really fruitful findings that came from it. But there are some other things I think we need to consider going forward. And so one of those things is that while you are, let's say, remembering this detailed face, there's also ongoing sensory input. So often we don't remember with our eyes closed, right? We don't recall visual details with our eyes closed. There's concurrent sensory input. And the other thing too is that in this case, instead of having a highly detailed representation, you can also have more abstract representations. So I could just recode this and say that this is John, and I don't have to remember what his face looks like. I can also just take some kind of abstraction of his face, which is in this case something like a smiley, and so on. So I want to go into these topics in three sort of sub-points that we'll go over in this talk. And the first is how information might be stored despite new sensory inputs. So this is basically the information that's coming from the eyes, what's happening when we try to remember visual information. All right, and so let's say you're still on your way to your meeting. You determined you did need a cab, and so now you're sitting in the back of the cab. You're trying to remember your friend's face, right? But at the same time, there's all this visual input. There's buildings, there's cars, there's all kinds of stuff happening around you. And the main point is that, as I already said, sensory input is often concurrent with memory. So memory doesn't really happen in isolation. Now, when we look at a lot of fMRI work that studied working memory in the past, paradigms often look like this, right? So someone is remembering, let's say, again, an orientation of a grading. And there's this long delay because it's fMRI and the bold response is slow, right? And then after that delay, subjects are doing something else. Let's say they're doing a two alternative forced choice. They have to say it's clockwise or counterclockwise, something like this, right? And what past work has found is that, especially in early visual cortex, including V1, right, the pattern of responses actually carries information about the orientation that's being held in memory. But as I already said, that's not much like the taxi cab example or most examples that happen in everyday life. And so somewhat more recently, some work has decided to show distractors during the delay and just sort of see what happens. And so they showed faces and gazebos. Oh yeah, I keep meaning to remove that last face there. That's Sirosh Interpodipat, and he gave us permission to use his images once upon a time. All right, and so this work thought, okay, well, you know, in everyday life, you have this concurrent sensory input. What happens when we show this to participants? And the overall conclusion from this paper is actually that, well, once you start showing visual input, then V1 doesn't really seem to hold that much working memory information anymore. And so the idea here is that sensory and memory processes cannot be concurrently represented in V1. Instead, these authors suggested that what happens is that memory sort of migrates to another part of the brain where it's held in a much more stable manner. In this case, it's superior IPS. And they suggest that this is though the primary storage site for working memory. All right, so this really got us thinking, right? Because if that is true, then this really changes our perspectives on V1 and its involvement in working memory. And then what is V1 doing and why would it be involved if there is no visual inputs and so on and so forth. So we kind of wanted to go after this and design some distractors that we thought would be really, really strongly driving V1 and therefore would really be distracting in V1. So what we did was design this task where, and I hope people can see my cursor, thumbs up, thumbs down, thumbs up, all right. So subjects see this little color cue, which is 100% predictive of what's going to happen during the delay. And they see this randomly oriented target, which you have to remember. And there's a long delay, 13 seconds, and then they rotate this bar to match this orientation that they have in memory. Right, during the delay, there's a distractor on the screen for 11 seconds. And in this example, this is a phase reversing Fourier filtered noise stimulus. So this is flickering like this for 11 seconds to really drive sort of distracting inputs to visual cortex. The second condition was a second grading with also a random orientation that's independent of this orientation, which will become important later on. And then as a third condition, we also decided to not show any distractors during the delay. Note that in this condition, we are really sort of optimizing our paradigm to find memory information during the delay, right? Because we also don't use a mask. So this really should be the condition where we find, if we replicate previous work, find information about the target orientation. All right. So we scanned 6 subjects. We put them in the scanner 3 times for 2 hours each. As I already said, the target and distractor orientations were random and also independent of each other. We collected 108 trials per delay condition. All right, then there was a second run that we collected in the scanner, which I'll call a mapping run. Suffice to say for now that this was used for two reasons. One, it was used to localize visually responsive voxels, and two, it was used as an independent training set for a multivariate model, which I'll go into more later. All right, so first, our behavioral performance or behavioral outputs impacted by these distractors. And we found that in fact, no. And so we tried to quantify this many ways we could. And this is again, a nice demonstration of how robust visual working memory really is, because imagine there's this 11-second task irrelevant, but still 11-second distractor on the screen. And subjects really do not seem to be impacted by this in terms of their behavior. All right. So did these distractors drive strong univariate fMRI responses as we wanted to? Just to orient you here towards the axis, this little sliver of gray here is when the target was on the screen. This big gray chunk here is when the distractor was on the screen, in conditions when there was one, of course. And this last gray panel here is where the response probe was on the screen, right? And so as you can see, especially in V1, the noise distractor was very, very good at driving visual responses, the grading distractor as well. And as you would expect, without a distractor, you just get a bold response to the target, which then sort of dies down here during the delay. All right. So what I want to talk about next is the multivariate model that we use to analyze these data. I want to preface this by saying that we also used a normal linear decoder and the results are pretty much the same. So I'll just show you this method, but you can use any other sort of multivariate method here. And the inverted encoding model, I'll go over this briefly, but it has two steps. The first step is the encoding model step, where you build your encoding model. So what we do here is we show a stimulus to the brain, and we measure a brain response, and we do that very many times for very many different orientations. And then we have this encoding model here, which consists of 9 idealized sort of channel responses. And then we relate one to the other. So here we have the response in each voxel J. And here we have a model channel response for each channel I. And then what we do is we solve for the weights. So we get a weight for each channel for each voxel, and that kind of looks like this. So when we have these weights for each voxel, which you can sort of think of as voxel preferred orientation weights matrix or something like that, right? Once you have this, you can move to the next step, the second step of the model, which is the inversion step. And so now what we do, we can measure a new response. So you can imagine on this last step, right, we use this training data, this independent mapping data. And here, instead of using, let's say, this localizer mapping data, you can use now data from a memory trial. So this is, let's say, a response that you collected during the delay of a working memory task. And you have the same ingredients here. Now you have the weights, you have a new response, and you can plug this back into this channel space. And then you can say, well, based on the weights that I've obtained from my model, plus the response on this trial, I would say that the orientation that people were remembering, or that this person was remembering, is, let's say, 84 degrees, right? Now, let's say you have a trial where you showed an orientation that was 126 degrees. You might want to center that on a common center, because across very many trials, of course, we showed random orientations. So on each trial, the orientation might be different. But once you center them onto a common center, you can look across all trials within a given condition and calculate this channel response. From here on out, I won't be showing channel responses anymore, but we will quantify the extent to which this is, let's say, a bump. Like if there was no information, let's say, about what you're holding in memory, then this channel response would be flat, right? So the degree that it's kind of curved, you can quantify this. And that's what I'll show next. All right. The other thing to point out is that unless, I start saying otherwise, what I will show you for now is that I'm using a model that was trained on this independent sensory data. So on a different set of trials from this mapping task, where a stimulus was physically on the screen, as it was driving visual responses, visual cortex. And then for the inversion or the testing part, we will use data from the memory delay. And so what this gives us is information that is available about orientation during the memory delay. All right. So what I'm plotting here on the y-axis is this quantification of, let's say, the bumpiness of this channel response function. I can go into this later if we want to. And on the x-axis is a bunch of visual areas along the visual hierarchy from primary visual area V1 all the way up to some IPS, so parietal cortex and more ventral LO1 areas. All right. So first we will look for the remembered orientation when there was either noise, grading, or no distractor present during a delay. And what we see is that throughout the visual hierarchy, including in area V1, there is a representation of the orientation that people were remembering. And there's no significant difference here between these three conditions. And so what we find is that despite this visual input that's driving visual cortex for 11 seconds, we can still recover the orientation that people were remembering during the delay. Now, another cool thing to point out is, of course, that we have this distractor condition where there is a second grading that is shown during the delay. And again, right, this is a distractor that's on the screen for 11 seconds driving visual inputs. And of course, we can also ask, can we recover its orientation? And the answer to that is, yes, we can, right? Perhaps unsurprisingly in V1, right, which is your primary visual area, so you should be able to see this orientation there. But we can do so pretty much, again, throughout the visual hierarchy. And one cool thing to highlight, I think, here is that while in V1, the response to a physical grading is still higher, not a response, right? But the amount of information to a physical grading is still higher than to what you're remembering. But as you go up the visual hierarchy, for example, area V3AB, this relationship flips, right? And so this is a hallmark of top-down processing, where this top-down memory process will be stronger in higher visual areas, whereas in V1, of course, you get a stronger representation for something that's physically on the screen. All right. So the other thing I think is really cool is that these representations actually persist over time. And here I'm just showing you area V1. This is again the same layout as earlier, right? Where this is your target, and this is your distractor, and this is your response epoch over time within a trial. And because we had 800 millisecond TRs, we could do this inverted encoding model at every TR. And what you see is that you indeed get this robust response that's then sustained throughout the delay and even shoots up a little bit here towards the end when people are starting to make their response. Now, when we look at the sensory stimulus, so this is your grading distractor, right? You see it's a little bit delayed, of course, because it's on the screen a second and a half later. But you also see that here, this is the time point where that grading disappears off the screen, and that a couple of TRs after that, you indeed see that there's no more representation of it. All right. Now, I quickly want to go back to what I said earlier about behavioral performance and that it wasn't affected by these visual distractors. But there's a little bit more nuance to that, I think. So one thing that I did in these data is that I chopped up people's data based on their behavioral error. So here, this is just an example subject. There's trials where they're doing really well, a little bit worse, and a lot worse. So this is the absolute error, right? So the bigger the error, the worse they are doing. And what you can do then is say, okay, for every single trial, I know which bin it is, best, medium, or worst. And what I will do then is, let's say the behavioral error was counterclockwise. I can then take the single trial channel reconstruction and also flip it so that everything is pointing clockwise now. The same I did here. Here I take the absolute error. I kind of do the same thing for the single trial channel responses, but I flip them based on their behavioral error. So now if you have a huge behavioral error, then presumably, if your channel response function also is biased in the same direction, you should see that its mean should also shift. And indeed, when we look at these channel responses, the average here for area V1, you indeed see that this is the case. So for the best trials, you see that the mean of the channel response function is about 0. But as you get larger errors, you see that also the mean of this channel response function shift towards larger errors. And we can quantify that, of course, by taking the circular mean, We can do this across the visual hierarchy, and you see that indeed behavioral errors track this neural representation, or at least a bias of these channel response functions. Cool. So this is just a little thing that I think is cool. So I'm not sure how familiar everyone is with the oblique effect, but I wanted to know, why does behavior vary? Why are people good on some trials and not on others? And it turns out that when you look at the very best trials, and you see at which target orientations were presented in this 1/3 of trials, right? You see that orientations around 0 and 90 degrees are overrepresented here. So that basically means that if you have an orientation that is vertical or horizontal, that people's responses are amongst the best of the best third. Hi, sweet cat.
Just want to say hi.
Oh, that's very sweet of you. Thank you. Vice versa here, when you look in the worst performance bin, you see the opposite, right? So when people are shown orientations around 45 or 135 degrees, their behavior suffers. This is just a little cool quirk, I think, of the D. All right. So indeed, cortical representations actually do track behavior. Now, another thing I want to show is that what happens when you increase distraction. So one suggestion, of course, we got from the reviewer when we submitted this was like, okay, well, maybe you should just use faces and gazebos. And we said, okay, we'll use faces and gazebos. Okay, maybe it matters. So we had this face gazebo condition, and we, again, included a grading condition and a condition without a distractor. The grading condition is slightly different from before, because before we were phase reversing our grading. Here, now we are flickering it on and off, and that has to do with matching the way we are presenting the faces and gazebos. Long story short, what happens now is that indeed we find a behavioral effect. So there is a deficit when people are seeing these face gazebo distractors, their memory performance suffers, also in the grading condition in this case, which might have to do with its flickering on and off. And what we see when we look in the brain is that this behavioral deficit, even though it's small, is really tracked by the representation that we see in basically all areas here. So you see without a distractor, the memory representation is pretty good in V1, but then with distractor, it drops a lot. So when we do impact behavior without distractors, so are the representations of visual cortex, so they are affected as well. All right, so to summarize this part, there is information in visual cortex about remembered items that is distractor resistant, right? And on the top of that, those irrelevant inputs themselves, so the irrelevant grading distractor is represented as well. And it coexists with this memory representation throughout the delay. All right, so what we suggest is that V1 has some kind of region-wide, let's say, multiplexing capacity where it can juggle information about inputs and memory, top-down memory as well. All right, so this is something I think is really cool. And something I want you to know more about is that, can this information be stored in multiple formats? And I'll tell you a little bit more what I mean with that. So what I've showed you before is that we had the sensory data right from this independent mapping task, and we use that to train our model, and we test on the memory delay. But really what we're training our model on is to recognize things that look like sensory-driven inputs, right? And this worked for early retinotopic cortex and LO1. What I haven't really shown is that it doesn't really work in parietal cortex. Which is strange, because this is of course not what the paper that inspired all this work, right? They suggested that the memory moves to parietal cortex, and we didn't see that using this method. To really drive this home, I went back and I looked in all over parietal cortex. So when I train on this sensory data, in both these experiments that I've shown, there really is not much in terms of memory information in parietal cortex. So if you just look at this, you would say, okay, well, parietal cortex apparently is not involved in memory, and from physiology and from univariate bold studies as well, we know that this is probably not the case. So what's going on, right? It's very possible that in some areas, including perhaps parietal cortex, and I wouldn't be talking about this if it wasn't so, right? That the representational format might be somewhat different from a sensory-driven response. So there might be memories in a non-sensory-like representational format. So how do we find those representations? Well, what we can do is we can train on the memory data and test on the memory data, right? And we do that through leave one trial out cross-validation. I'm not going to show you what happens in V1 through V4 because, you know, if the format is, even if it is sensory driven, if you train on a sensory driven format from the memory, it will work, right? It will naturally work onto itself. But the question, of course, is what happens in IPS when we take this approach. And I kind of already spoiled the surprise, I suppose, but what happens when you train on the memory data itself is that you see really robust representations in all over parietal cortex, basically. And the cool thing here is that there are no differences between these memory conditions, but also not in the second experiment where we did see a dip with behavior, right? And so it does appear that parietal cortex really has a robust representation, despite that there is some interference. The other cool thing here is, of course, these gray bars. This is, again, the sensory distractor. So the sensory grading that's physically on the screen. When we train on that and we test on that, we don't find information about it in IPS. So it appears that IPS is really doing whatever is on task. It's doing the memory, but it's ignoring what's on the screen, and therefore we do not find information about it. All right. So there is probably a non-sensory-like representational format. So we know what it is not, right? We don't know what it is. All right. So yes, memory information can be stored in multiple formats. And we know that there's a sensory-like code that is similar to a sensory-driven response, and that there is a code that's somehow transformed away from the sensory-driven response, even though we might not quite know what it is. All right, now lastly, I want to talk about what happens to mnemonic contents when sensory inputs are attended, right? And again, to give a demonstration, let's say you were unable to get a cab, which is common in New York, but you rented a moped instead. Now you're trying to recall your friend's face. But in this particular instance, you can't just zone out and let the sensory input passively enter your brain. You have to look out for cars and other mopeds and bikes and so on and so forth. All right, so what kind of inspired this work was a study using these laminar probes and recording a multi-unit activity in the V1 of macaque. And this comes from de Roos lab. And what this method allows you to do is compare, let's say here, the input layer, layer 4, with the superficial and deep layers. And the superficial and deep layers are the layers that are known to receive input or feedback, basically, from the rest of the brain, whereas layer 4 is kind of your input layer from the eyes, right? And so what they had these monkeys do, they did a line tracing task. So monkey is fixating, and there are a bunch of lines, like squiggly lines, and the monkey has to figure out which one is attached from the fixation to, let's say, an endpoint and a dot. And when it figures that out, it mixes a cut to that dot. So what happens when a monkey is doing this task is that you see it is, by the way, it's fixating, right? So it has to attend this line while it cannot move its eyes, right? So we see that layer 4 is receiving some input, right? Because there's lines on the screen. But you see in these superficial and deep layers, you see that there is an attentional modulation. So there is an increase in response as the monkey is doing this line tracing task. So this is kind of an attentional modulation, if you will. Now, they had a second condition where they showed the same stimulus display, but they very quickly took it off the screen. So now what the monkey had to do is it had to mentally trace this line, whereas the line was not on the screen anymore. So it had to do it from memory. So this was a sort of a memory condition. And when they recorded, they see that in layer 4 now you don't really see much activity anymore because there's also no input drive to these neurons, right? Because now the screen, it doesn't have lines, and so it's empty. But you still see that in these feedback layers, there's this modulation. So what you're seeing is that both in attention and in working memory, you see this feedback modulation of these superficial and deep layers. And what that sort of suggests is that these two top-down mechanisms, or these two top-down domains, are drawing on the same cortical structure architecture. And if that is the case, then if you have to do them concurrently, you might start seeing some interference here, because if they're trying to use the same parts of the brain to do this task, then they may not be able to do both at the same time. All right. So this is very similar to the previous task. And we want to just kind of see what happens when you start attending now a distractor, right? And so what happens here is that on every single trial, the distractor is always a grading. So for 11 seconds, you have this phase reversing grading again. The only difference between the three trial types now is this cue color that happens very early on. And there's one of three colors, and so one of three instructions. So in this case, subjects are ignoring the distractor that's being presented during the delay. But there's two other conditions. So when you look at this distractor, right, it's phase reversing, but sometimes you might see it change its orientation, and sometimes you might see it change its contrast as well. And so that happens on every single trial. But on 1/3 of the trials, subjects are attending the contrast changes, and they're reporting it as they go along. And on some trials, subjects are reporting the orientation changes. So they're seeing a contrast increase or decrease, or they're seeing an orientation clockwise or counterclockwise. All right, so we ran this also in the lab, so not in the scanner, to look for what this does with subjects' behavior. Right. What's nice about lab, of course, is that we can have 14 subjects that come in day after day and do like very many trials, because these are long trials, so these are long experiments. And what we see is that this is the bar when subjects are ignoring, right, ignoring the distractor. And when they start attending either the contrast or the orientation of the distractor, you see that the absolute error goes up. So their performance is basically worse. At the time that I made this slide, we had 6 subjects data collected. I think we have 9 now. And so this at the time was not quite significant because we have, of course, far fewer trials in the scanner. But you see that this similar behavioral error is found in the scanner subjects. So there's an increase in behavioral error when subjects have to attend the distractor. I am personally still amazed by how small this increase in error is, because for 11 seconds, they are diverting their attention and they're constantly monitoring the stimulus because the changes are probabilistic. So they have to do it throughout and they cannot kind of stop. And these are undergrads at UCSD. And I still think this is kind of just an amazing demonstration of how robust visual working memory really is and how good people are at this task. All right, so what happens when these sensory inputs are attended? Well, first of all, let's look at the bolt response again. In V1, we don't see any differences between these 3 conditions. And I want to highlight that because the changes are happening in all 3 conditions, in terms of sensory input, these 3 conditions are identical, right? But we don't see a modulation with attention in V1. Whereas when we go to V4, which is kind of known for more, bolt-related attentional differences, you do see that here now you have when you can ignore the distractor, and with the attention condition, you see indeed that there is a heightened bolt response in V4. And I think this is where things get really cool. What happens is that when these memory representations, when the distractors are attended, memory representation is decreased. Right, so when they ignore the distractor, still pretty good. They start attending contrast, it becomes a little bit less. When they start attending orientation, it becomes even less. Now, we have the sensory stimulus itself as well, right? So this grading that's on the screen. And here we see the exact flip of this effect. So when subjects are ignoring, of course, you still get a good representation of V1, right? Because this is like an 11-second visual cortex driving thing there. But when they start attending the contrast, you see that there's an increase in how much information you can see. And then when they're attending orientation, this is increased even further. All right. So what happens to mnemonic contents when sensory inputs are attended? What we see here is this clear trade-off between these competing cognitive demands, which really implies that they're drawing on the same underlying cortical structures. All right, so then hopefully all of these studies together will give you a little bit more complete picture of what we know about visual working memory and sensory recruitment theory in the brain. So first of all, we saw that with sensory inputs, you can still have memories in V1, and they can have them concurrently with these sensory inputs. Although, once you start seeing behavioral deficits, you also start seeing that these areas have, somewhat diminished amount of information. And we also looked at the abstraction and basically the different formats in which working memories can be represented. And so presumably IPS is doing something that's not sensory driven per se, or not visual like. I'm using quotation marks. I hope everyone can see that. Air quotes. Of course, because we don't know exactly what it's doing, right? But we know that there's probably some abstraction taking place here, because if you have, let's say, a huge full field orientation grading, and you want to remember, let's say, every pixel in that image, that's a bit excessive, right? You can do some massive dimensionality reduction on that, because in orientation, you can represent that also, let's say, as a Cartesian coordinate or something like that. I'm not saying that that's what's going on, but there certainly are formats that you can use that are less costly than involving all of visual cortex. All right, so I want to thank my collaborators, of course. So this work was done in the lab of John Srenses, together mostly with Chaipa Chunharat, who's now a professor in Bangkok. And these are some of the lovely undergrads who did a lot of the behavioral work that went along with the studies I've shown you. I haven't shown all of it, but they've ran many, many, many subjects in the lab. And I couldn't have done this without them.